Okay, if you can hear me, can you just comment? Can you comment in the comment box below? So we'll be looking at more questions on more like exam focused questions on this course. All right. So if you can hear me, just indicate. Just say you can hear me. Okay. So as I did earlier on, just mention the question. I would read out the question, then we would also comment from there, give you the answers, then also give explanations to the respective questions. Okay. So in the previous one, we had a break in transmission, so we're able to put together this one. All right. Okay. So basically, would continue from what we're looking at. We're focusing on organic chemistry basics, and we'll also proceed with other questions as well. Okay, we've been able to treat mixtures and also some other aspects as well. Okay. All right. So basically, hydrocarbons are compounds made up of dash and dash. So because we have carbon, major what makes them hydrocarbons is that they are made up of carbon and hydrogen. Okay, so these are the major components that makes hydrocarbons what they are. All right, so basically, by virtue of the general definition of organic chemistry, it's the chemistry that studies organic compounds, which are of course the carbon containing compounds. Okay, the carbon containing compounds. All right, so basically these are generally what the organic compounds are, and as well the fact that they're also obtained from plant and animal sources. Okay, they're also obtained from plant and animal sources is another crucial information that you must take cognizance of, you must take note of. All right, so the simplest hydrocarbon is methane. All right, and methane is CH4. All right, that's the simplest hydrocarbon. All right, that's methane because it's more like a compound that has the ratio of 1:4. Okay, 1 carbon to 4 hydrogens. All right, there is no other hydrocarbon that has the molecular formula that is as simple as this. Okay, so that's why we call it the simplest hydrocarbon. All right, simplest hydrocarbon, and most especially also because it contains carbon and hydrogen. All right, so that's it. So now another question: atoms other than carbon and hydrogen in organic compounds are called dash. So you remember we said that the major constituents are carbon and hydrogen. All right, so when we say the ones that do not contain, like the ones that are not carbon and hydrogen, basically. All right, so what are they called? They are called heteroatoms. All right, so they are called heteroatoms, and of course examples include oxygen, nitrogen, sulfur. So these are typical examples of heteroatoms. All right, so oxygen, nitrogen, sulfur are examples of heteroatoms. So any anytime they are found in organic compounds, they are not carbon and they are not hydrogen, so they are called heteroatoms. All right. Then another question, we have alkanes contain only dash bonds between carbon atoms. So if we have, let's say, we have want to draw ethane, structure for ethane. So ethane is basically containing carbon to carbon single bonds and 3 hydrogens. All right, 3 hydrogens. We have hydrogen here, we have hydrogen here, we have hydrogen here, we have hydrogen here, we have hydrogen here as well. All right, so this is the structure of ethane. One thing we need to understand is that if you look at this structure, you realize that they are all single bonds here. All right, they are all single bonds here. So that's one thing that is peculiar to alkanes. They contain single bonds. All right, they contain single bonds between carbon atoms. Now look at carbon to carbon atoms bonded by single bonds. All right, so basically they are also what we call saturated. They are called saturated hydrocarbons. They are called saturated hydrocarbons. All right, so it's important to take note of these crucial explanations of what they are, what alkanes are. So don't forget that they are all containing single bonds. The next question here, alkanes are said to be dashed because they contain maximum hydrogen atoms. So like I said, they are also called saturated hydrocarbons. So they are said to be saturated, all right, because they contain maximum hydrogen atoms. That's one thing about them. So the presence of the single bond here makes it possible for alkanes to have more atoms than other compounds and other hydrocarbons. Okay, so it's something very crucial that you must note. Okay, so the next question here is: carbon forms dash bonds in organic compounds. All right, so we have what we call tetravalents. Okay, tetravalents. So, but basically, this is not actually the answer to the question. The answer to the question is that carbon forms 4 bonds. Okay, so carbon forms 4 bonds. All right, so we tend to have a common carbon atom when it's linking with hydrogens. For instance, methane linking with hydrogens here. The basic thing that has to be taken cognizance of is that if you look at it very well, you realize that we're having 4 hydrogens here, and each of them are linked towards carbon with single bonds. All right, so this is what we call the tetravalency of carbon. So this is the tetravalency of carbon, the ability for carbon to attain a tetravalent nature is called the tetravalency of carbon. All right, so now the next question: a ring structure in organic chemistry is indicated by the prefix cyclo. So whenever there is a ring structure is more like a cyclic shape. So we could have something like this. Now, so this is a ring structure, a cyclic structure. So this is called cyclohexane. Cyclohexane. We can have something like this. Can have something like this as well. Okay. Can have something. Then maybe it stops here. Something like this stops here. If you look at it very well now, you see that these dots here are the number of carbons. These points, every junction here, the number of carbons. So this one have 5. So this is cyclopentane, all right, because it has 5. All right. So now we could also have another one containing 8. 1, 2, 3, 4, 5, 6, 7, 8. So in this case scenario, considering that we have 8 sides, so we automatically call it a cyclooctane. So basically, these are just examples of cyclic hydrocarbons. Okay, these are examples of cyclic hydrocarbons, and as a matter of fact, they have a ring shape. This is a ring shape. Okay, this is a ring shape, that's why we call them, or a ring structure, that's why we call them cyclo. Okay, all right. So basically, if we have alkanes, okay, I'll just be briefly explaining to you how we name alkane structures. All right, how we name alkane structures. All right, so let's say we have a common alkane with substituents. Now the steps that are usually applied in naming alkanes, okay, are as follows. Number one, the first thing that you have to do when you're naming an organic compound is to count the longest continuous carbon. Count the longest continuous carbon chain. Count the longest continuous carbon chain. What this serves is that this serves as the parent name of the structure. All right. Number two, the second thing is to number the chain. Number the chain to give the substituents. Number the chain to give the substituents the smallest possible number. Smallest possible number. All right. Then thirdly, the next thing you have to do is to attach numbers to the substituents. Attach numbers to the substituents based on their position in the chain. Based on their position in the chain. That's the third step. Then the fourth thing you have to take note of, after attaching numbers to the substituent based on the position, their position in the chain, is that now for substituents which appears multiple times, such as 2, 3, and 4, we use prefixes. Use prefixes such as di, tri, tetra, respectively. This tetra, respectively. The another thing is that another thing you need to take note of is that naming. Another thing is that naming is done in alphabetical order. It's done in alphabetical order. That's one thing you need to note. When you're naming organic compounds, you name them in alphabetical order. And another thing is that number 6 is that numbers are separated. Numbers are separated from letters. Numbers are separated from letters using hyphen. That is the normal, what you know as dash. Okay, while numbers are separated from themselves using comma. Okay, what you know as comma. All right. Then while naming, we name in lower cases. That it means that every name in the structure must be in small letters. It's very compulsory that you must name in lower cases. All right. So there should not be capital letters. There should be no capital letters of any sort. All right. So like I said, count the longest continuous carbon chain. Number the chain to give the substituent the smallest possible number. Attach numbers to the substituent based on their position in the chain. So for substituent which appears multiple times, such as 2, 3, and 4, we use prefixes such as di, tri, tetra, respectively. So naming is done in an alphabetical order, and numbers are separated from letters using hyphen, while numbers are separated from themselves using comma. So we name in lower cases, that's small letters. All right. So now basically, these are the steps. Okay. Now another thing I need you to note is that for alkanes, when we say alkanes, they are that parent name I was talking about, okay, are based on the members. All right, based on the members of the alkane group. We have methane, we have the octane as well. We have propane. We have butane. We have pentane. We have hexane. We have octane. We have before octane we have heptane. Then octane. Then after octane we have nonane, and lastly we have decane. All right, we have decane. So basically, for methane, if we have CH4 as the molecular formula. General molecular formula for alkanes, we have CnH2n plus 2. So ethane is C2H6, propane is C3H8, butane is C4H10, C5H12, C6H14, C7H16, C8H18, C9H20, and C10H22. C10H22. Right, so these are their molecular formula. So it's important to note that. All right, now basically, if we have structures, all right, and we intend to name them, it's important to actually name them following the major rules. And initially I made mention of substituents. I talked about substituents. Now, common substituents for alkanes are the halogens and also the alkyls. I'll tell you what, the halogens, they actually act as the group 7 elements, which of course they are. We have chlorine. Chlorine is Cl, but we call it chloro. Okay, bromine is Br, we'll call it bromo. All right, iodine is I, but we'll call it iodo. Then we also have fluorine. Fluorine is F, but we'll call it fluoro. All right, so these are halogen substituents. But now for the alkyl, substituent, alkyls are actually formed by the removal of one hydrogen atom from an alkane. And we have the methyl. Methyl is CH3 with a bond. We have ethyl. Ethyl is C2H5 with a bond. We have propyl. Propyl is C3H7 with a bond. All right. We have butyl. Butyl or butyl is C4H9 with a bond. So usually, if you see this C2H2 H5 rather for ethyl, sometimes it can be written as CH. So that it can be written as CH3, then CH2 bond. That's for ethyl. All right, CH3, CH2, then bond. Okay, then bond. Then propyl is CH3, CH2, CH2, then bond. All right. So basically, these are substitutes. I'm putting this bond here because they are usually attached. All right, they usually serve as attachments. All right, usually serve as attachment. So now, quickly, what we'll be looking at, moving forward, what we'll be looking at now, we'll be naming some common structures. And the aim is to ensure that we have a good background or a good knowledge of naming alkanes. All right, so basically, if we have something like this now, one thing you need to understand now is that for hydrocarbons we could have a straight chain and we could also have a branched chain. Okay, here we could have a straight chain and we could have a branched chain. So now, if we have, let's say we have CH3, then we have CH2, then we have C here, and we have CH3, we have CH3 as well. Then at the top here, we have CH2, and we have CH3. This is structure 1. Then structure 2, we have CH3, we have C. Then we have Cl here, we have CH3 here, we have C, CH3, CH, CH2, and CH3. Now, if we are to name these two different structures, beginning with the first one, now the idea is to count the longest continuous carbon chain, okay? For a chain to be continuous, it means that it has to continue linking. The carbon-to-carbon bonds must continue linking, all right? It must continue linking, okay? So, by the time we count like this, 1, 2, 3, 4, look at the straight chain. Remember, I told you that it can be straight, it can be branched. So now look at the straight chain. If you look at the straight chain, you realize that there are 4 carbons in the straight chain. All right. So when we are considering this, you have to consider a chain that links. If you look at this now, like from like this to here is a chain. Like this to here is a chain. Like this, even the straight chain is a chain as well. All right. So what do? We count 1, 2, 3, 4, 5. 1, 2. If you look at now, the longest is 5, but the straight chain is 4. So it means that we have to take this one that is 5. So usually when we get the straight chain, what we do is to barricade it like this. Okay? Create a barricade. Whatever is outside the straight chain is called the substituent. Whatever is outside the straight chain is called the substituent. All right? So basically, if you look at this straight chain, one thing you need to understand is that as we have 5 carbons in the straight chain, it implies that it's called pentane. This is the parent name. This is the parent name of the structure, pentane. Another thing we must identify is that these ones that are outside the chain, all right, these ones that are outside the chain are called the substituents. And if you look at it, what we have here is CH3. We have CH3, and I told you that CH3 is called methyl. Right? I told you that CH3 is called what? Methyl. So the fact that CH3 is called methyl, and I told you that if we have more than one of the same substituent, we use prefixes like di, tri, tetra, like that. So now here we have what? We have methyl. So what do we do? What do we do after getting the chain? The next thing now is to if you look at now, these two substituents are attached to one carbon, the same carbon. Both of them are attached to the same carbon. Look at this bond. Look at this bond attached to this carbon. So the reason why they are called substituents is because they are outside the chain. I'm overemphasizing it. All right, because they are outside the chain. Okay. So now what we need to do is if you look at the chain now, we have this end and we have this other end. So what we have to do is to number from the end that will give these substituents the smallest possible number. Number from the end that will give these two substituents the smallest possible number. So now, when we are numbering, take note of only the carbons that contain the substituents. So if we start counting from here, we have 1, 2, 3. Now this particular carbon here is carbon 3. From here, this particular carbon is carbon 3. And there are 2 substituents. So these 2 substituents, now you write the position of the 2 substituents, and 2 of them are attached to carbon 3. So you say 3, 3. Because 2 of them are attached to carbon 3, you just say 3 plus 3. So we would add this 6. Now check from this end as well. Check, remember a chain has only 2 ends. Check from this end now and count. 1, 2, 3. These 2 substituents are attached to carbon 3 from here. If you look at it now, both of them are attached to carbon 3. From here, 3. From here, 3. Just a coincidence. It's not like it happens all the time. So even from here, 2 is also 3 plus 3. So both of them are 6. So we can decide to choose from any end. Okay, we can just take number from here. So after you have to realize that both of them are the same, and both of them are the same substituents, okay, we can number from any end. Now let me let you know something. If both of them were different substituents, one thing you need to note is that you would actually pick a direction that will give the substituent that comes first alphabetically the smallest number. Don't worry, we'll come to that. Okay, but both of them are the same. Okay, that's why we can just choose any end at all, because both of them are the same, and from here they are both at carbon 3. From here they are also both at carbon 3. All right, so what we do, we'll now we'll put our 1 here. 1, 2, 3, 4, 5. So it means that the name of this structure will be 3,3-dimethyl pentane. All right, the parent name will always come at the end. All right, the parent name should always come at the end. If you look at it very well, you realize that I did not put any space. There's no space here. So that's how you're supposed to draw your structures as well. It should be without spaces. If you look at it very well, you realize as well that there are no capital letters here. They are all in lower cases. All right, they're all in lower cases. So it's important to note that. All right, so this is the name of the structure. This is the structural name. Now let's look at this particular one as well. Let's look at this particular one. If we count the longest continuous carbon chain, now first of all, the reason why I use dimethyl is because there are two substituents. If there were three actually of the same substituent, you use tribe, there were 4 tetra. All right, but they're actually 2, so that's why I'm making use of di. All right, that's di. Now if you look at this structure, you realize that the straight chain has 5 carbons. The straight chain has 5 carbons. So for that we must name it based on the number of carbons. So that is that 1, 2, 3, 4, 5. It's also called pentane. So the parent name is also pentane here. Parent name is also pentane. So that's the parent name. So like I told you, whenever you identify your parent chain, what you just have to do is to simply barricade it. Anything that is not in the parent chain is a substituent. All right. Now the reason why we do not come down like this is because if we had done 1, 2, 3, 4, it's still lesser than the parent chain, which is 5, which contains 5 carbons. Are you seeing it? All right. So basically, we have to number this chain so the substituents can have the smallest possible number. So now let's start from here first and check 1, 2. If you look at it, you realize that these substituents are carbon 2. So let's say 2 plus 2. Then let's move to the third substituent. So the third substituent is carbon 3. So we say 2 plus 2 plus 3. All right. Like I told you, whenever you are trying to check the numbering, the major purpose of numbering the chain is to know the exact positions, the perfect positions of the substituent. Okay, so know the perfect positions of the substituent. So the general idea is to number from any end that will give the substituent the smallest possible number. So if we should not start from here now, we have 1, 2, 3. So we have 3. This one now will be at carbon 3, and these two substituents will be at carbon 4 respectively. So this will be 3 plus 4 plus 4. Now between these two, now you realize that this one has smaller numbers, because if you sum this number, you have lesser numbers than this one. All right, so 2 plus 2 plus 3 will give you 7. 3 plus 4 plus 4 will give you about 11. So it means that we have to number from here. So by the time we number from here, we have 1, 2, 3, 4, 5. All right, so now what it implies now is that the name of this structure, we'll take it in alphabetical order. Look at this. This guy is chlorine. All right, this guy is chlorine. So this guy comes before these other guys here. Okay, here we have methyl. So C comes before M. So in alphabetical order, it means that the name of this structure will be 2-chloro. Okay, 2-chloro. Then these two substituents here are called methyl. So 2-chloro. Then these two substituents are methyl. So, and this one is a carbon 2. Why this one is a carbon 3? So you put hyphen. You say 2, 3 hyphen again. Dimethyl what? Pentane. Dimethyl pentane. So like I say, it has to be in alphabetical order. C comes before M. So you have to write your chloro first. So it's important. And I said that the parent name comes first. Okay, someone is asking, okay, you'll be a bit confused on the second one. All right, so okay, let me explain that again. All right, so the basic idea is this. Like I said, get the longest continuous carbon chain. After that, you identify the position of the substituents in the chain. Identify the position of the substituents in the chain, after which you have to number the chain to give the substituents the smallest possible number. All right, number the chain to give the substituent the smallest possible number. All right, then now when you're naming, the one that comes first alphabetically, C comes before M. That's why I'm putting 2-chloro. Chlorine is a carbon 2. All right, so that's why I say 2-chloro 2,3 dimethyl pentane. All right, 2-chloro 2,3 dimethyl pentane. All right, That's it. All right. So now, let me draw another structure. Okay. Let's say we have something like this. We have carbon, like CH3 here. We have C. We have CH2, CH3. All right. Then we have CH2. Here now we have Br. Okay. Then we have CH2. Then we have C, and we have CH2, CH3. Then we also have CH2, CH3 at the top. All right. Then here we have CH3. Now look at this structure. Okay. How exactly do we name this structure? If you look at it now, you realize that it's not really like the contemporary ones we did in number 1 and 2. Now the idea basically here is that, as I explained earlier, you get the longest continuous carbon chain. Okay. Now the continuous carbon chain must not necessarily be the straight chain. That's what I objected initially. It must not necessarily be the straight chain. All right. It can actually be a branched formation. Now check this. Now check the straight chain. We have 1, 2, 3, 4, 5, 6. It's not the longest. If you look at it, this is the longest. 1, 2, 3, 4, 5, 6, 7, 8. You can actually go from down here and come. So basically, if you want to draw a structure, if you want to draw a structure, or let me even focus on name. You want to name a structure based on the diagrammatical illustration. The idea basically is that you can number that particular chain from any end. You can number it from any end. You can count it from any end. If you count from here to here, we're having 1, 2, 3, 4, 5, 6, 7, 8. And this happens to be the longest. So we have to barricade it like this. Okay? Then anything that is not part of the parent chain is a substituent. So look at me, look at how I'm circling the substituent. All right? Now, you notice that I did not circle CH2 separately from CH3, provided that they are bonded together. It means that it is one substituent. You take it as one substituent. Besides, there's no alkyl substituent as CH2. There's no such alkyl substituent as CH2. Alkyl substituent begins from CH3. So remember what I told you about CH3CH2. What did I say CH3CH2 is? I say CH3CH2 is what? Is ethyl. All right? And that's what we have here. So this is ethyl. This is the second member of the alkyl substituent group. This still remains our CH3, which is our methyl. This is bromo, this is methyl. So now the idea now is to number the chain from the end that will give the substituents, these substituents here, the smallest possible number. All right? So now if we are to number from, remember we have two chains, we have two ends now. If we are to number from this end, now we have to number from this end. This will be 1. Okay? This will be 1. Now, there's no need writing it yet. Let me just number it. 1, 2, 3. These two substituents are carbon 3. If you look at from here, these two substituents are the third carbon. If you start counting from here, these two substituents are carbon 3. So let's say 3 plus 3. Because there are two substituents. That's why I'm writing 3 plus 3. They are numbered. So when you're treating substituents, you treat them individually. All right? So 3, 4, 5, 6. Why these two substituents are carbon 6? So we say plus 6 plus 6. All right, now let's check from this end. 1, 2, 3. 3, 3 as well. 3 plus 3. 4, 5, 6. Plus 6 plus 6. If you look at it very well now, you realize that both numberings, both directions are giving you the same what? The same number. Just like what we did, or what we had in the first case. I think that should be the first case, yes, that we had 3 plus 3 and 3 plus both sides. All right. So that is here now where we named this. So that's the same situation we are facing here. So what do you actually do in this kind of scenario? Like I said, the only time you would have to pick any side at all to take as your numbering pattern is when you have exactly the same substituent. Look at now, we have different substituents. We have methyl here, we have bromo here, we have ethyl, we have bromo. So now what do you do here now? You take the direction that will give the substituent that comes first alphabetically, the smallest possible number. Let me repeat myself. Now, you take the direction, that is the direction you would number from, will be the direction that will give the substituent that comes first alphabetically. For instance, now this is methyl. Methyl begins with an M. Bromo begins with a B. Ethyl begins with E. Methyl begins with M. So among these four substituents, you realize that bromo comes first alphabetically, which begins with a B, amongst all of them. So what do you do? What you do is simple. Like I said, you have to pick the side. If you now look at it very well, you now realize that it is from here that bromo will be will have smallest number. But from here now, bromo will be 6. So from here, bromo will be 3. So since you're having the same numbering on both sides, so the idea, the rule is that you have to now take the side that will give this bromo. All right, take the side that will give this bromo the smallest number. So it is from this side. So this 1, 2, 3, 4, 5, 6, 7, 8. You can now number all the carbons now, but the major purpose of numbering is to actually know the best position for the substituent. So this is actually the best numbering, considering the fact that it is from here that your bromo will have the smallest possible number. So that's the rule. So now if we are to name this now, alphabetically, bromo will come first, and bromo is a carbon 3. So we say 3. We say 3 bromo. 3 bromo. Up next is ethyl. Ethyl. Ethyl is a carbon 6. So 3 bromo, 6 ethyl. 6 ethyl. Then look at our 2 methyls. Methyls are carbon 3 and 6 respectively. So this time around, we put a hyphen and write 3,6-dimethyl. Remember, the parent name will be octane because it has 8 carbons. So 3 bromo, 6 ethyl, 3,6-dimethyl octane. So this is the name of the structure. All right. So this is the name of the structure. All right. So this is the name of the structure. So basically, this particular rule only applies to when you number both sides of the chain, and it gives you the same numbering. But if you have the same substituents, okay, if you have the same substituent in the chain, all right, if you have the same substituent in the chain, then you would have to use any pattern, like any direction at all. Okay, you have to use any direction. All right. So basically, let's look at more questions. Let's look at more questions under this. All right, more exam focused questions. Okay. So now we have to now look at some calculation problems. Okay, so we'll not spend a lot of time only focusing on organic. All right. So now I also want to let you know that there's a technique which is called fractional distillation. All right. So it's used to separate substances based on the differences in their boiling point, which is also known as vapor pressure. All right, vapor pressure. So I'll be looking at a couple of questions. All right, I'll be looking at a couple of questions right away, and these questions are calculation questions which you must take cognizance of. Now, number 1, how many moles of hydrogen atoms are present in 3 moles of water? Okay, so how many moles of hydrogen atoms are present in 3 moles of water? Okay, now first of all, the compound here is water. All right, compound here is water. Now if you look at it very well, you would realize that if we should split this, if you look at it very well, you realize that if we should split this, we have 2 hydrogens. That is, we have H2. Hydrogen is diatomic here. All right, so it means that we say 1 mole of H2O, 1 mole of water is equals to, if you look at it very well, is equals to 2 moles of what? Of hydrogen. Okay, 1 mole of water is equals to 2 moles of hydrogen. Okay, and the question says how many moles? So they say how many moles are present in 3 moles, how many moles of hydrogen atoms? So if 1 mole of water, because water is 1 mole here, but hydrogen has 2. So if we have 1 mole of water here and equals to 2 moles of hydrogen, so you say how many moles of hydrogen will be in 3 moles? So you now say, so 3 moles of water will now be equals to x. Will now be equals to x. Because now we'll now be looking for the number of moles of hydrogen that will be equivalent to 3 moles of water. Since we know that 1 mole of water is equals to 2 moles of hydrogen. So now when we make x to a formula and we cross multiply here, so we'll now say 3 times 2 divided by 1, which will give us 6 moles of what? Hydrogen. So that's our answer. So it means that we have 6 moles of hydrogen in 3 moles of water, considering the fact that 1 mole of water will give us 2 moles of hydrogen. So that's a very crucial thing that we must take note of. All right, that's a crucial thing we must take note of. So now let's look at the next question. Okay, let's look at the next question. All right, so how many moles of hydrogen atoms are present in 5 moles of propane? How many moles of hydrogen atoms are present in 5 moles of propane? All right, look at propane here. Propane is C3H8. All right, this is the molecular formula for propane, and the question is how many moles of what? Hydrogen atoms. So now if you look at it very well now, you realize that 1 mole, in this case now, 1 mole of propane, 1 mole of C3H8 is equals to how many moles of hydrogen here? 8 moles of H, hydrogen. Hydrogen is 8 here. So they are now asking that how many moles of hydrogen will be present in 5 moles. So it means that 5 moles of propane now will be equals to x. We want to know how many moles of hydrogen now will be 5 moles. So please do it in this form. So x now will be 5 moles times 8 moles. 5 moles times 8 moles divided by 1 mole. Mole will cancel mole here. 5 times 8 is what? 40. So your answer is 40 moles. All right. So your answer is 40 moles. Okay. So it means that you have 5 times 8. So you have 40 moles of what? Of hydrogen. All right. So that's the basic idea. That's the idea here. All right. So we'll be looking at another question. All right. So the question here is on limiting reactants. All right, limiting reactants. So it says, given the reaction, remember I told you in the previous class that the limiting reagents or reactants are reactants which are completely used up in the course of a chemical reaction. All right. So if we have, let's say, 2Al, okay, plus 6HCl, this reaction to give us 2ACl3 plus 3H2. So now the question now is that if 4 moles of aluminium reacts with 6 moles of HCl, the question is determine the limiting reagent. Determine the limiting reagent. All right. So this is very simple. Now, solution to this question. Now, if you look at this now, you realize that aluminium is reacting with hydrochloric acid to form AlCl3. We have AlCl3 here. AlCl3 plus H2. All right. AlCl3 plus H2 rather. So now if you look at this very well, now basically, how do we get limiting reagent? I told you that limiting reagent is the one that is completely used up in the course of a chemical reaction. Usually they tend to give the mass of the reactants. But yeah, now they gave us the moles of the reactant. All right, the moles of the reactant. So when you have moles like this, it's very simple. So what you just have to do is to divide each of the moles by their stoichiometric coefficient. So for Al now, aluminium has 4 moles. So divide 4 moles by 2 moles. Divide 4 moles by 2 moles. Moles will cancel moles, you have 2. All right. Aluminium has 2 as the molar coefficient. All right. So divide the number of moles. If you are given mass, you have to divide the mass by the molar mass to get the number of moles first before you divide by their stoichiometric coefficient. Now for HCl, now our major focus is aluminium and hydrochloric acid. So HCl has 6 moles. So 6 moles divided by 6 moles. These 6 moles I'm writing is gotten from this. So 6 divided by 6 is 1. So which one is the least? Okay, the least is hydrochloric acid. So I didn't tell you this, okay, but take note of it. The one that has the smallest ratio, okay, is the limiting reagent. So HCl has 1, so it means that HCl is the hydrochloric acid is the limiting reagent. Hydrochloric acid is the limiting reagent, and it will be the one that will be used up in the course of the chemical reaction. Okay, so what you just do, divide. You will definitely be given a reaction like this. So divide by their coefficients. All right, divide by their coefficients. Okay, you're only focusing on here. That's your only focus. You're only focusing on this reactant side. Okay, then now paraventure they told you to calculate theoretical yield. Paraventure they say you should calculate theoretical yield. All right, so basically theoretical yield, you have to understand the definition of theoretical yield. Theoretical yield is the amount of products that is formed in the course of a chemical reaction, the amount of product that is formed in the course of a chemical reaction. All right, so that's the theoretical yield there. And theoretical yield is actually expressed in grams. All right, it's more like the mass, the total mass of the products that is formed. All right, so subsequently I'll give you the formula for that if when we have a question that has to do with that. Now, so the next exercise before us here, okay, the question says okay, now the question says, okay, if the theoretical yield of AlCl3 is 4 moles but actual yield is 2 moles, calculate the percentage yield. All right, if theoretical yield is 4 moles, for instance, if it is expressed in moles, but usually it tends to be expressed in grams. So you are being told that if the theoretical yield is of AlCl3, if it is 4 moles and its what's it called? Let me take the question. The theoretical yield of HCl4, but its actual yield is 2 moles. This is the theoretical yield. Let me denote it as Ty. Why this actual yield? So how do we now get the percentage yield? How do you get the percentage yield? So the formula for percentage yield is simply this yield here, which is the theoretical yield, divided by the actual yield. All right, then times 100. Okay, or most times it's actual yield divided by theoretical yield. Yes, so we have most times we tend to divide the actual yield, like I think I've said this before, actual yield by theoretical yield, yes, multiplied by 100. So the actual yield here is 2, theoretical yield is 4, multiplied by 100. So this is 1/2 times 100, which will give us 50%. All right, 50%. So it's actual yield over theoretical yield, not the other way around. All right, so it's important to note that. So usually if you are given a question of this sort, you'll be given the values for the actual yield and as well as the value for the theoretical yield. Okay, so it's important to note that. All right, so don't forget that formula. Okay, so moving forward, if we have a question like say calculate the molarity of a solution, calculate the molarity of a solution containing 2 moles of sodium chloride in 1 liter of solution. So calculate the molarity, okay, calculate the molarity of a solution that contains 2 moles, okay, that contains 2 moles of NaCl in 1 liter of solution. 1 liter of solution. Now, one thing you must note is that when we say molarity is basically the ratio of the number of moles, and volume, okay, volume of solvent or volume of, most time volume of solution though. All right, so the number of moles here, we have 2 moles divided by 1 liter. All right, so 2 divided by 1 is 2 mole per liter. Sometimes it's denoted as mole per dm cube. Mole per dm cube. All right, so the answer there is 2 mole per dm cube. Or sometimes this mole per dm cube can be denoted as molar, 2m, capital letter M. All right, so you see mole per liter, mole per dm cube, molar, they all mean the same thing. All right, they all mean the same thing. All right, so that's it. Okay, so now let's say we have given another question. Say how many moles of solutes are present, how many moles of solutes are present in 0.5 liters, how many moles of solute, you are looking for moles, are present in 0.5 liters, volume is 0.5 liters, 0.5 liters of a 2 molar solution. Molarity here is 2 molar, and you're looking for moles. How many moles? All right, how do we detect this? So it's very simple. So we know molarity, we say molarity is the ratio of number of moles and the volume. I'm looking for number of moles here. So what do? We just substitute. We say 2 equals to the number of moles here is unknown, so let's call it x. Volume here is 0.5. all right, so to make SOA to a formula, we just have to multiply this, cross multiply. So 2 times 0.5 will give us 1. all right, so 2 times 0.5 will give us 1. So we have 1 mole as our answer. Are you seeing how easy it is? Okay, so 1 mole as our answer. So that's it basically. Now I also want to let you know this. So I also want to let you know this as well. Now you can be given the molarity of the substance. You can also be given the molar mass of the substance. Okay, molar mass of the substance. You can be given the volume as well, and you'll be told to calculate the mass. Okay, you'll be told to calculate the mass of that substance. Now I want to break this down for you. Now you see this molarity that is equals to moles per volume. This moles we have here is basically the mass divided by the molar mass, right? We've stated this. So it means that we can say that molarity of the substance can be the mass over the molar mass, all divided by the volume. All right, so we can be told to look for mass in some cases. So what you just have to do here is that if we want to make mass or to a formula, mass is simply molarity times molar mass times volume. This is the formula for mass. That's if you're giving molarity, you're giving molar mass, and you're giving volume. Just multiply through and you get the value for the mass. All right, get the value for the mass. So that's the very simple formula to actually use. Okay, all right. So another thing Another thing I need to let you know of is, okay, like I said, that combustion, I said it earlier. Don't forget combustion formula that I say is CXHY, which is plus x plus y over 4O2, which will give you XCO2 plus y over 2 H2O. All right, plus y over 2 H2. Okay, but that being said, we'll look at the next question. All right, so the next question is, how many hydrogen atoms are present in 3 moles of butane? How many hydrogen atoms? You use that first explanation that I gave, okay, to solve this. So you attempt it. Now the next question, draw the structural formula of propane. Propane is C3H8. So the structural formula is just simply 3 carbons, all right, which have hydrogen here. We have hydrogen. This is structural formula for propane. 3 carbons, 8 hydrogens. All right, so you link these carbons with another carbon to carbon bonds, then the sides that are left, if you look at this carbon now, has up, left, right, up, down, up, left, right, like this. All right, so you replace them with hydrogens. So that's the pattern. You replace them with hydrogens. Okay, it's as simple as that. Okay, so you see how many single bonds are present in methane. I told you that for alkanes all have single bonds. All right, so if they say how many single bonds are in methane is like this structure of methane. All right, this structure of methane. So this hydrogen. If you look at it, we have 4 bonds here. Okay, we have 4 bonds here. Okay, so that's it. All right. Now there's another question. Say write the general formula of alkenes. Now general formula, I told you the general formula for alkanes is CnH2n plus 2. Now, but for alkenes, it is just CnH2n. For alkynes, it is CnH2n minus 2. All right. So this is for alkanes, this is for alkenes, this is for alkyne. All right. So these are their molecular formula. So you say the general, write the general formula for alkenes. So this is the answer, CnH2n. All right, CnH2n. All right. Then for a typical alkene, say draw the structure of ethene. If you want to draw the structure of a double bonded organic compound, like alkenes are all double bonded. So ethene is like this. There are double bonds between the 2 carbons. So there are double bonds between the 2 carbons. So both of them have only 2 hydrogens. 2 hydrogens each. That's why we say C2H4. Both of them have 2 hydrogens each. All right. So please take note of this. So C2H4, 4 hydrogens, 2 carbons. So this is the structure for ethene. Now, the pattern for naming alkenes is that when we are naming the structure, we must consider the what? Must consider the position of the double bonds. All right. Must consider the position of the double bonds. And okay, if someone asking if there's any AOC, so basically, okay, like I said earlier, you have to focus on, you have to study organic compounds. You have to study the chemistry of solutions that I did in previous video. You have to study acids and bases as well. You have to also study electrochemistry. I also made a video on thermochemistry as well with solved exercises. All right, with solved exercises. So you also have to take a look at chemical bonding that I explained thoroughly, to provide diagrams of level structures and all of that. All right, so that's it. So this is for C2H4. All right, so I'll be stopping this particular video just so I can save it for the sake of other persons who probably didn't start with us. Okay, then we'll most likely, or we may resume another live session. All right.